Alright, hello guys. So I'm just gonna go over Dijkstra's algorithm. So I'm gonna explain how Dijkstra's algorithm, I don't even know how to say it, but I think it's Dijkstra's algorithm. And so I'm gonna go over just how to do this. So the first thing I'm gonna start with is I'm gonna be looking over the whole entire algorithm, how to use this algorithm. Basically, to do this, to find the shortest path from the source vertex to every other vertices in a graph and a undirected graph for this problem. And the problem that I'm solving is basically this one. This is this is what the code would look like. So we start here. So we start with the algorithm steps. So we want to start by setting all distances to infinity except for the source should be set to 0. So depending how we're going to do this, so I have an example to walk through too. So looking at the data structure we'll use, the first one is, so the one I'm talking about is distances. I already set this to 0 because for this example, I guess I forgot to say this. Oops. But for this example, the source is equal to 0. Okay. So this is the first thing we did. We create this list, and the length of it is like that. So we set all distance to infinity except the source is set to 0. Create an array for visited and set all to false initially. So we're going to keep track of visited nodes. So here we have them all equal to false. Then we want to create a priority queue like a min heap. Push the source to it first. So you see this thing? I forgot to add this. So I'm going to need the min heap. And the first thing that's going to be pushed to it will be the 0 and the 0 because that's the node. Node 0 has 0 distance. Okay. Loop through the min heap and pop out the elements with the least and pop out the elements with the least priority, which is also the smallest distance so far. And then the fifth step is a check if it's already visited. If so, just continue to the next iteration. Also add it to visited and go to step 6. Okay, so you just check if it's visited. There's no reason to visit that node again. If the current vertex distance plus edge weight is less than the vertex distance in the distance list or array, then you want to update the distance and push it with the new distance into the min heap. Repeat the process until the heap is empty. Okay, so those are the steps. So let's do an example here. So this is an undirected graph with adjacency matrix. So here's the graph, undirected edges, as you can see. So undirected just means that it goes from, the edge is pointing from 0 to 1, and it's pointing from 1 to 0. And then this is the representation of the adjacency matrix for this, and you can look at this. I'll look at a couple points on it, but look at node 0 and node vertex 1, vertex 0 and vertex 1, and it should have an edge weight of 4. A 0 means that there's no edge, and also 0 shares an edge with the 7 as well, with an edge weight of 8. And also you can even go down to 1, and you say, well, 1 is shared with 0 here. So you can see this is I don't know what the word is described, but there's some type of symmetry in this matrix. Okay? And so this is the adjacency matrix representation. So this is everything initialized. There's one other thing that I'm keeping track of for this problem, because for this problem you want to print out the path, the shortest path. So I'm going to keep track of parents. For every node that I visit, I'm going to look at where did I come from previously. So we'll see how that works by going through the example. But so the first thing we'll do is we'll start with the source node. And So we'll visit this node here, 0. And when we visit it, we're going to want to check that it's not, we'll see it's not visited, we'll set it equal to true because we're visiting it. And we pop it out of here. So basically we're popping it out of the min heap. And then we're going to go through here, and then we look at each of the, we look at its edge weight, which is 4. So we take the current vertex, which is 0, its current weight distance is 0, plus 4 is 4. And we check that that's basically smaller than the distance currently for vertex 1, which is infinity, which it is. So we'll update this to 4. We'll do the same thing for 7. So 7 is 0, 1, 2, 3, 4, 5, 6, 7. So it'd be here, which is also true. 8. And then you also add in the parents here. So we're going to say that the parent for 1 is 0, and the parent for 7 is 0. And then for the min heap, we'll pop in the distance 4, and 1, and 8, and 7, and this would kind of be the order too. So then the first thing we do is we're going to move along. So we move 2. So the first thing we pop out is going to be the 1. So we kind of move over to the 1 node, and we're going to visit this. So everything I blue circled we visited. And so when you visit this, it's going to turn the 1 here. It's going to see we haven't visited yet. It's going to turn to true. It's going to pop it out of my min heap. My bad. I just forgot that the problem I'm solving is different. This problem, there's a, so bad. So bad. I just realized that there's a destination for this type of problem. So let's say the destination is 4. I mean, this is different than some problems. Okay, so I'll go over the destinations actually afterwards. So first I'm going to do this. So right now I'm solving this problem, which is find the shortest path from the source vertex to every other vertices in the graph. Okay, so it goes to the 1, right? And it turns this to true. And then it's going to look at its places it could go. So it could go to 2. And if you add 4 plus 8, you get 12, which is less than infinity. So you're going to update distance, and you're going to add it to here with 12, and the vertex is 2. And you're going to say the parent for this is, the parent thing doesn't really matter right now. I'm going to keep track of parent because I'm also going to solve 2 problems here. I'm going to say, what if I have a destination equals to 4, right? So I'm trying to find the shortest path to 4, and I want to print out that path. So anyways, we go to the 1, and then we want to basically look at the other edges. So it's also connected to 7. We look at, but the thing is that if we do 4 plus 11, that's 15, but that's greater than the 8. So we're not even going to update that path. We're not going to want to take that path. It's not as good as going from, it's like if we want to return the shortest distance to 7, we'd rather take the path that's only 8 distance from the source. So we're not going to update, we're not going to add that in here. So then we go to the next iteration. We're going to visit the 2 over here. And so we're going to mark this as visited. And okay, so we're just do true. Wait, what? I did that wrong. Why did I do that? I don't know why. My bad. We're not going to go there. We're going to go to the 7 because it's the min next. So we're going to go to the 7. And when we go to the 7, we're going to pop it out. There. And we're going to set 7 to true. So, whoops. Okay, so set this to true. And then once we do that, we're going to look at everywhere that is connected. So it's connected to 1, but the distance is like 19, which is way larger than the 4. We're going to ignore that. It's connected to 6. the one where it's connected to 6 with a 9, I'm going to definitely add that in here. So that would be 9 and 6. And also, if I add this in here, 6 would be here. It's going to be 9. And then also, I'm going to go to 8. So if I go to 8, the distance will be 8 plus 7, which is 15. So 15. I'll add that one in here as well. 15, 8. I forgot to add parents. But basically, the parents for 2 is 1. Okay, so the parent for 8 is 7. Okay. And the parent for 6 is 7. Okay, that's how it is right now. So that's cool. Now we're going to go to the next one. I marked as true. Okay, so we're going to go to the next one. So we're going to pop up the element with the smallest value, which is the 6. So we're going to go to 6 next and visit it. And by visiting 6, we're going to set it equals true. And we're going to pop it out. It's currently 9. Actually, I'm going to keep this in here, but I will pop it out. But yeah, it's 9, right? So I have to remember it's 9. And then we can go to 8. 9 plus 6 is 15, which is the same good as the previous one. So here it depends how do you want to break ties, and and I mean, I guess that depends, like, how do you want to break ties. So I think for this problem, you break ties by, let me see, it says smaller index should be preferable. Okay, so smaller index is preferable. Sure, so I have to add in some logic for basically saying that it should prefer the 6 over the 7. So we will update this to 6 just because it's a smaller node, I guess. So we'll update the parent, but that's all we really have to update. And then to 8, sorry, I'm at 6, right? So I'm at 6. I can also travel to 5 from 6. And if I travel to 5, that's 9 plus 2, 11. So this will be, since it's definitely smaller, we'll add it here. And we'll add this in here as 11, 5. Okay. Cool. So then what we'll do is we'll travel to the 5. So we're going to visit the 5, set this equal to true. And then if I do that, I'll remove this from here. And the 5 can travel to the 4, which is with, I guess, with 21. So with 21, right? So this would be 21. And the parent for the 4 would be 5. Something weird is going on. I think I forgot to do the parent for the 5, which is 6. Yeah. Okay, and then, so that's going to the 4. So we have to add that in here. So it's 21 to the 4. And then we also can go to 3. Distance to 3 is the 10 plus 14, so that's 24. Sorry, wait, what did I say? It was 11 though, right? So it's 11, so it's 25. So it's 25, so I'll add that to our thing. 25, 3, and add the parent for 3 to be 5, and we can also travel to 2, but I don't think we're going to want to do that because that'd be 15, and we already have 12 here, so yeah. So we're not going to travel to that. So the next thing that we would remove would be the 2. So we're going to travel all the way up here to the 2 next and visit it. So we'd pop it from here. I won't pop it yet because I'm going to keep it. But yeah, I'm just going to mark this as true. And then when you travel to the 2, what we want to look at is basically we can travel to 8, right? And when we travel to the 8, it'd be 12 plus 2, which is 14. And we look at what our current travel to the 8 is. It's actually cheaper than this 15. So we will basically do that, and we'll update this to 12, and we'll update the parent to 2. So like all I'm saying is that it's actually cheaper to travel to the 2 and then travel to the 8. And then if you do that, then basically, sorry, it's not 12 though. It's definitely not 12. It's 12 to travel to the 2, right? It's 14. Yeah, it's just one better. 14. Okay. And then 2 is also connected to the 1. But since that's in visit already, like, we're not going to, like, worry about that. Well, it actually just won't be shorter. Like, yeah, you can travel to the 1, but you add this 8 to the current 12, and you get, like, 20, which is, like, we already know we can travel to 1 way cheaper. Also, I messed up earlier, didn't I? Because when I was at the 1, I said I could go to 2 or 7, right? But the 1 could have also went to 0. But it would have been, of course, a higher priority. Oh, I missed that. Okay, but anyways, this is just getting like 2. That's okay, that's okay. So this 2 goes to the 1. The 2 goes to the 8. Or the 2 can go to the 3, right? And if it goes to the 3, we'd be adding 7 plus 12, which is like 19. But we already know we can travel to 3 with 25. So actually it is better. So we'll add this in here. We'll add that we can travel to the 3 with 19 costs. And we'll add, instead of using that, we'll travel from the 2. And this gets lowered to 19. And basically just exhausted this. Okay, so the next one we're going to look at is the one with the smallest value, which is, it looks like it's 8. So we're going to go to 8 next. And basically, we're using this one, so I'll pop off this one with 14. So at this point in time, I look around, right? I look around at my 2, and I say, okay, take 14 plus 2, that's like 16. Or like you look at 2, 12. Okay, well that's larger. Take 8, look at your 7, which is 14 plus 7, which is definitely going to be larger than 8. 14 plus 6 is definitely going to be larger than 9. So basically, you don't travel anywhere. So you're done there. So then you go and pop off again. So this time it will probably try to remove this 8. Did I forget to set this equal true? I did forget to set it equal true. In fact, everything has been visited except for the 3 and the 4. Okay, so then we go to 8 and we say, well, hey, we've already visited 8, so we're not going to visit it again. Okay, so we're done. Just move forward. So that's the use of the visited, just to like get rid of stuff that appears again that you've already visited. You've explored all the edge weights at a lower cost too. So there's no reason to look at higher cost. Now the next lowest one is this 19 and this 3. So I guess we'll go to the 3, well, we go from the 8. So we go here. And at the 3, basically, we're going to mark this as true. We're visiting the 3 right now. From the 3's perspective, 3 is 19. We can go to 4. 19 plus 9 is what? 28. It's kind of larger than the 21 we already have. So probably not going to update that. Not going to update to the 5. Not going to update to the 2. Yeah, so this is just gets popped, and we don't really use the 3. Then we go to the next value, which is this 21 and the 4. So then we go to this one, and we mark this equals to true. And we look at the 4. We can travel to the 5. We can travel to the 3. None of this is going to be cheaper though, so you know, whatever. So we just remove it. And then we keep going. We want to go until the heap is empty. So when we pop off the 3, we're like, we look, it's already true, so we just skip. We don't even bother doing anything. Okay, so now we're done. Okay, so what's a cool feature of doing this? So notice this parents array is kind of going to be useful for keeping track of the path to each of the nodes. So let's say our problem, we want to find the path to the vertex 4, right? So let's look in parents, and we can create a function that'll do this. But let's look in parents and look for the 4th element, so 0, 1, 2, 3, 4. So it says a 5. So let's say 4, and so let's add this to some path. And I'll add the 4 first, that's my end node, and I'll add the 5. Why do I add the 5? Because that's what is at the index position of 4 for parents I. Then it says go to 5, so okay, so I go to 5, which is 6. Okay, so I add 6. Sorry. Wait, I went 0, 1, 2, 3, 4, 5. Yeah, so I went to the 5, which said 6. So then I have to go to 6, which takes me to 7, which then takes me to 0, which is also the source. So to get the path, so the path is 0 to 7 to 6 to 5 to 4. That's saying it's the cheapest. And notice the cost for going to node 4 is 21. So let's add them up. So if we go 0 to 7, we have 8. Then we go 7, we have 6, we have 9. We go 6 to 5, we get up to 11. And then we go 5 to 4, we get up to 21, which was the cheapest distance to get to the shortest path to 4. Any other path costs more, and that's pretty nifty. And we can do this for anything. That's the path for 4, but we could also find the path for 3 if we just start at the 3rd index and then follow its parents as well. So that's how you can get the path as well. So from this, you can get the path to any vertex, and you've calculated the distance, the shortest distance to every vertex. This is within an adjacency matrix. Now, in this problem, this is what the code looks like is this. So I'm going to try to go through this code a little bit, maybe make it a little more clear. So, so this is just dealing with the inputs for the problem. Nothing really big here. Creating an adjacency matrix and everything and doing that. And then so here's the function itself, the Dijkstra thing. So I take an adjacency matrix, I take in, which is like the size, source, and a destination. So for this one, you have a destination vertex. So okay, like we did before, we first pop the 0 and the source. And then we do visited equals to false. So we set everything equal to false for in, which is the number of vertices. Sorry, yeah, in is the number of vertices. And then we set the distance equal to infinity, but we set it equal to 0 for the first element. So all the rest are infinity. Technically, it's not the first element, it's just a source element. Yeah. So it just says 0 for the source element. I guess I had made a mistake there. And I set the parent to -1. The -1 is just being used. Why am I using -1 and this multiplication, which creates basically it creates copies of -1 value for n times. So it'll be an array of n length of the number of vertices. But the -1 is just basically to say that if you reach -1, you've reached the beginning of a path, or like you just have to stop there. That'll come in handy for a function later. Okay, so then we do while the heap. So this is the thing where you want to do it while the heap is not empty. So you get the current distance, and you get the node from the heap. So you pop out the one with the heap, of course, is a min heap, so pop out the thing with the lowest current distance. You check if it's been visited or not. If it hasn't been visited, set it equal to true. Okay, so here we start iterating through. Basically, when you look at the matrix, you're iterating through this entire row. So like, I see the 4, I see the 8, so that means it shares an edge with 1 and 7, and I need to, you know, add those distances. So we get basically the edge weight, so the vertex that we're currently at, and the I, because we're searching through the I here. So it's basically just like, you know, it's like, oh, if I'm at vertex 0 and I'm searching through here, and I get a hit right here, I get something that's basically, if it's equal to 0, just continue. I get a weight that's like 4. I'm like, okay, cool. So the weight is 4 to go to this I node. So take the cost plus the weight. This should be current distance. So you take the current distance plus the weight, and you see, is that less than the distance to that vertex right now that this one's connected to? If it's not, if it is smaller, then you want to update the distance. And there's one other thing I'm going to do, by the way, which is, so there's one thing I want to check, which is if it's equal, by the way. So elif cur dist plus w equals dist I. And you want to update if basically if I is less than, well, yeah, you want to update the parent if v is smaller than the current parent I, if the vertex is smaller. This is just that breaking the ties, which I didn't do before I realized. So if the vertex you're looking at right now is smaller than the current parent vertex, which is saying like you're coming from a smaller vertex, then you actually want to replace the parent I with the v. So that's just breaking the ties. But here, this step is taking updating the distance matrix array, updating the distance array, then updating the parent array, and then pushing this into the heap. And then, you know, so you keep doing this while loop until basically the heap is empty. And then what you want to do is you want to print out the distance to your destination for this problem. And then for this problem, you want to print out the path from the parent array to that destination. So the parent path, print path, basically is doing this. It takes that parent path, and we create a path, an empty list. We create a node for our destination, and we basically are going to while loop through as long as our node is not equal to -1, and we append to our path the current node. And the current node is based off the parent. So it just goes, you know, it just keeps going to where, let me see, how do you represent this? So it's like it's going from one to another. Like you know, it's like for 4, right? So 4 was 5, so it says 5. So I set my next node equal to what 5 is, and I go to 5, and I set my current node equals 6, and I go to 6, and it says 7, so then I go to 7, then it says 0, so I go to 0, which is equal to -1, so I stop. That's like what this is doing. So it's like I keep appending to my path, and then I keep updating my node based off of like where does the parent of your current node lead to. It says, it'll say, maybe it'll say like go to 5. So it's like, okay, we'll go to 5 next. So I append 5, then I put in 5. I say, well, the parent at the index 5 says go to this node, and maybe it'll say go to -1. And if that's the case, it breaks the while loop, because now it's equal to -1, and that means that you've reached the beginning. And then I just have to use this trick for Python, which is I want to invert or reverse the path, and then this is just joining it and converting everything to a string, and yeah, that's it. So submit. So see if this will work, and also okay. Also, real quick, since I did this example, let me try